Okay, so I hope you uh, used the last week to go over the existing material again and do exercises and so on. So today we are talking about template Haskell. Last lecture was about generics, which is also a way of metaprogramming, and template Haskell is the other way. So again, metaprogramming is basically programs that write programs. And so generics, as I said, is one way, but template Haskell is another way. And in template Haskell, it's more literally true. So basically at compile time, these so-called templates are executed and generate code, and that code is then spliced into the other code of your program. So we'll introduce template Haskell, in particular typed template Haskell. There's also an untyped variety. We'll talk about that and about the main mechanisms of using that, quotes and splices, and also so-called stage restrictions. And similar to what I said about generics in the last lecture, using template Haskell is much easier and more common than actually like creating it yourself. So as I said, for generics, it's very common that you have some custom data type and want, for example, JSON serialization for it. And then you can just use the generics easily by just adding it, derived generics to your deriving clause to get support for your code, for your type. So you don't have to write the generic code yourself. And similar is true for template Haskell. So a lot of libraries, including lenses, for example, have support for template Haskell. So you can automatically derive like lenses for your own types without having to write the template Haskell code yourself. But in this lecture, we'll talk about both. And to motivate it, we start with an example, namely how to cleverly implement a power function. So that takes, I mean, this is somewhat anyway. So the idea of power is it takes the second argument to the nth power, where nth is the first argument. So and do that efficiently. So ignore this for time being and just make it disappear. So power, for simplicity, it's from int to int to int. You could, of course, also use like arbitrary precision integers, which actually I actually don't like it like this. Let me deviate from the slides. I prefer it like this. So I'm not sure whether we had natural before. I think probably we did when we talked about parsing, I think. So it's arbitrary precision natural numbers, so non-negative integers. I think this is the appropriate type for this actually. So we have an n and an x, and want to rise x to the nth power. So the naive implementation, let me just, I don't know, let me call it naive power. Would be if, sorry, just a second. If n equals 0, then that would be 1. And otherwise, it would be x times recursively naive power n minus 1 x. I mean, that's basically the definition of power, right? So we can try it in the REPL. Naive power. I mean, it's the other way around. I mean, normally it would be, the arguments would be the other way around. But on the slides, it's in this order for whatever reason. I mean, it will become somewhat clear later. So for example, rising 2 to the 10th power would be 1024. Of course, we can also rise to the 1000th power, and that's quite a big number. Haskell is so fast that you don't really see a problem here, performance-wise, even with large numbers like this. So 10,000 or even 100,000 probably still works fine. Let's try a million. Okay, that takes some significant time in the REPL. Probably I should interrupt it. I just wanted something that's like, let's try 200,000. Okay, that's a very large number. Anyway, so that's just the definition. You multiply x n times with itself. Now, of course, there is a more clever algorithm. That's the one on the slide. So let's try that. And here the idea is, so again, if n equals 0, it's 1. So as before. But now we make a case distinction whether n is even or odd. So if n is even, I mean, we can use the fact, I mean, these power laws. We have x to 2m is x raised to the mth power, the second power. So that's like high school. So we can use that here. So that would be this. And if it's odd, I mean, here the rule would be, if I have something odd, then I can still do x to the mth squared. And then I need to multiply with the x as well. Okay, so if you implement this, you basically do the same. Let's check whether that's the algorithm on the slides. No, it's not. Okay, so on the slides, it didn't do this. It just does it naively. So it just uses x times. So basically what we had in the naive case, or n minus 1x, sorry. Okay. Can try that out. It also seems to work. Yeah, and that looks faster, right? I mean, than what I had before. Okay, so that has nothing to do with metaprogramming, of course. The idea is just that we would like to optimize. And let's now say that we always want to take 10th powers, or I mean, for a fixed n. So we want to do something like power 10, integer to integer. Something like this. And ideally, because now the 10 is known, we know exactly which of these cases here would hold, right? And So one should think that at least when the compiler optimizes, that it would make use of this information. So for example, it knows now the n is fixed 10. So it's always the second case. So we always have to do x to the fifth power first. And then recursively, we also know, okay, so then in the recursive call x n is 5. So we have to compute the fourth power and so on. So ideally, we would hope that the compiler somehow unwraps all of that and has like an optimal implementation for raising something to the 10th power. So let's go back to the slides. I mean, okay, it works. Right, so I mean, this is basically what we want. But if I basically by hand do this, so if n is 10, then n is even. So we have let y equals power 5x in y times y. Sorry, y, x. So I just basically did this by hand. But now the 5x, so if n is 5, then we are in this case. So we have to compute the fourth power. We just say how it's done. Okay. Right. So let me also do it like this. Sorry. Right. So the 10th power is p5, the fifth power times the fifth power. The fifth power is x times the second power times the second power. And the second power is x times x. P10. So this was would basically be unrolling this recursive definition by hand for the special case that n equals 10. And hopefully that still works. So power 10 to that's power. Right. So yes, so if we know, the point is if we know n basically at compile time in advance, then we can use this algorithm here and unroll it, specialize it for n equals 10 to get this efficient implementation. Or well, it should be efficient, right? I mean, this looks very efficient. But question is, if we don't do this work, if we use our original definition of the power function, is the specialized version faster or not? And I mean, if you did all the exercises, then probably there was one about benchmarking, but maybe you haven't. So let's look at the main program that I wrote here. Right. So there's if we look at the if we look at the Cabal file, I use this criterion package, and the criterion is one of several package packages that you can use for benchmarking. So with criterion, sorry, get back to the main program. There's something called bench, and you give it a label, and then in principle the computation you want to benchmark. There's this NF here, and that is I mean, I don't know whether you did the exercise or not, but the problem with benchmarking in Haskell is that Haskell is a lazy language. So I mean, if I do something like this, let me see. If I do something like x equals 10 to 1, 2, 3, 1, 2, 3, 1, 2, 3, or I can use my power function. So let's say power 1 billion of whatever, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I now press enter, it immediately returns. And the reason is that Haskell is lazy. So even though this is an insanely large number, this executing this line doesn't almost doesn't take any time because Haskell is lazy, so it doesn't actually compute it. It will only compute it if the value is actually needed. So if I now like want to display it, then I will have to wait for a very, very long time, probably, until I see anything. And it will, okay. So I can't even interrupt it. Okay, fine. Anyway. So the point is benchmarking is not as straightforward as in other languages because of laziness. Because I mean, maybe the work is not done and something like this would immediately return. So in these, for example, in criterion, in order to get proper benchmarks, you must somehow force Haskell to evaluate the value actually. And this NF does that. So there's a type class involved, NF data. Don't really have to go into that. I think it suffices to say that, suffices to say that NF data is for types that can be, where it makes sense to say something is fully evaluated. So for numbers, for example, it does make sense for integers. You just evaluate the, sorry, that question?
Okay, no, I think someone just
by accident unmuted. Okay. Right. So this NF basically evaluates that or forces it to evaluate. And so I just did that. So let me import power. And let's take whatever, 42 to the 10th power. Then let's use our power function. And let's use this specialized one that we handcrafted to be specialized for the power 10. Sorry, and then of course I have to, sorry, this. No, why this is so weird. Maybe it's on purpose for didactic reasons. And this power 10. Why is this now complaining? Hmm. Okay, fine.
You need
Oh,
to say
sorry.
the file. Yeah.
No, so the NF, actually, I mean, we must look at the type of NF. So it takes a function and an argument and then benchmarks it. And what NF does is just think. It will completely evaluate the sorry. So this NF takes a function and an argument. And the power is just the built-in power function. But the built-in power function has the arguments in the more natural order. First, the thing you want to take to a power, and then the exponent. So that's why I flip it here. Right. So that's this. And now let me run this. What did I call it? Sorry. I called it templates. Okay, great. Let me save and let me run it. Cabal run templates. Sorry that I must just comment some stuff. That's for later. Try again. Okay, so this criterion, this benchmark tool, it will run, I mean, it's quite sophisticated. So, I mean, this 10 to the power of 42, the example we are using here, is of course not sorry, 42 to the 10th power is not a very large number. So that's only some microseconds that it takes. So this criterion package will automatically run the same computation many times to also get an average value. So now let's look at it. Right, so the built-in one takes 13.39 nanoseconds on average. Our power function, the clever one, takes 97.76 nanoseconds. And if we specialize, so if we by hand do that we specialize it to 10, it's 3 times faster. It's 32 nanoseconds, but still 3 times slower, frustratingly, than the built-in from, I mean, this caret here, this operator is in the standard libraries. In particular, this one here, if we don't specialize the 10, is much slower than the one where we do specialize the 10. Let me just check one thing quickly. Yes, so I also, this minus -02 here in the GHG options means that I enabled optimization. So the GHG is trying to optimize. And one should think, and I mean, we have never talked much about how GHG works and what optimizations it does, but one of the things it does do is inlining. So it should do things like recognizing that because the 10 is fixed, it should be able normally to inline this and somehow do something similar that we did here by hand. But the point is, or the problem is that GHG doesn't inline recursive functions, and this power function is recursive. So therefore, I mean, one should hope that a clever compiler can basically make those two equally fast, but it doesn't. And the reason is it's recursive. So basically the goal now is to use meta programming to achieve something like this, but without us having to do it by hand. So we want to write a meta program, a program that writes programs where we can basically, for a fixed natural number, a fixed exponent, produce something like this code, but without having to do it by hand. And then hoping to get similar performance to this handcrafted one that we did here. So that's the motivation where, I mean, one example where meta programming is useful, if you can do some compile time optimization. If you know you will always raise something to the 10th power to automatically like get optimized code like this without having to do it by hand. Okay, so that's the goal. Right, so yeah, we have the same observations. So this unrolled version, the power without 10 by hand optimized. I mean, the optimized version is significantly faster than the unoptimized one, and the built-in one is even faster. I mean, this always depends on which GHC version you use, and maybe also on the types, because on the slides it's for int, and I used it for natural int. I mean, for us it was not just slightly faster; it was like a lot faster. And the built-in one was again 3 times faster than this other one. But sorry, this other one. But nevertheless, we have the same order of, I mean, the built-in one is the fastest, and the one where we by hand unrolled the 10 is the second fastest, and the one where we didn't do it by hand is the slowest. And of course, if we did something, I mean, maybe just for fun, I should also do the naive. Sorry, let me just do naive as well. Why doesn't that work? Pray. Sorry. It should be even slower, I hope. We also see that, I mean, there's quite a big error. So we do get different results now, but like roughly it's still the same. Now let's see the naive. Yes, that's again almost 2 times slower than this one we had here. Okay, right. So the situation is we have this algorithm for better exponentiation. If we basically make use of the fact of this power law that taking something to an even power, we can take it to half of that exponent and then square the result. And we can actually do it manually, like for example, for 10, where we did it by hand to get better performance. But if we implement that like in code, like we did with this power, then we get even worse performance. And as I already told you, the reason is that GHG doesn't unroll recursive functions. So the fact that we know we will only apply the function where the first argument is 10 somehow doesn't help us. And so this is now where type or template Haskell comes in. And that template Haskell first appeared in 2002, so it's more than 20 years old now, in the paper template Meta Programming for Haskell. And then there was an extension called quasi-quoting, which will get to at the end of this lecture as an example. What I like about Haskell, one of the things I like about Haskell is the papers always have these nice names. So why it's nice to be quoted, quasi-quoting for Haskell. And finally, we got typed quotes and splices in 2013. And we'll talk about those mostly in this lecture. And the goal is to give the programmer more control over what happens at compile time and what at runtime, and to eliminate boilerplate. I mean, an example for boilerplate is, for example, these lenses, where we said it's very boring to write lenses for record types. It's easy but boring. And template Haskell gives us a way to eliminate that. And this power example is an example for the first type, where we know that some computations or optimizations could already be done at compile time. And we would like to make GHC do do certain things at compile time already. And the one fundamental term or concept in template Haskell is quote. And a quote is used to build a piece of syntax. So basically piece of code or syntax tree. And as I said, we will talk about typed template Haskell mostly. And in that case, it's not just some arbitrary code, it's code that is of a specific type. So let's start with a very simple example. If we just have an expression of type int, I mean, this is just like week 1, lesson 1. Let me just anyway do this. So let's go back here. So x1 int and plus 1. So I mean, this is just the integer 2. There's nothing new to this. X1 is just 2. Okay. But now using template Haskell, we can do something like these weird things, and they are called Oxford brackets, or actually, I mean, it's like a square bracket and a vertical bar. Those two would be called Oxford brackets. And the second vertical bar is for type template Haskell. I have no idea how you pronounce it, like typed Oxford bracket or something. And then it's no longer an integer, an int. It's something of type code q int, and it doesn't represent the number 2. It represents this piece of code, 1 plus 1. So let's first see whether I can actually do this. So x2 code q int x2 these weird brackets, 1 plus 1. Okay, and for this to actually compile, sorry. Let me just remove this again first. So this code queue is defined in language.haskell.template.haskell, and I think that's not part of the base libraries. So actually you need this template Haskell package for this. So that's defined in the template Haskell package. And you also need the template Haskell quotes extension for this to work. And now one problem is if I now do x2, then it doesn't have a show instance, but the type is as promised on the slides, code queue_int. There is a way to actually show it, so that's what I hit here. So you can, there's this queue monad, we will talk about that a bit later. But anyway, so in this queue monad, you can actually get a show instance. And there's also a pretty printing way. So I defined these two helper functions. So if we do show code exp2, so this is like a very verbose way of representing this piece of code 1 + 1. So this basically says it's an infix operator, namely the infix plus operator. And the two arguments are the integer literal 1 and the integer literal 1. This pp code helper function that I defined is nicer because if we do this, we basically really see this piece of code 1 + 1. The only ugly thing is that the plus is qualified. So this is where the numeric plus for int is actually defined in ghg.num. But nevertheless, so right. So this is a normal int, but by putting some piece of code into these Oxford brackets, we get a piece of code, and it's typed. So this is piece of code that basically represents an int. Okay, so this is like the most fun, and this is called a quote. So we quote code. Right, and now, I mean, this is one thing, but now actually, what do we do with these pieces of code? And so we quote code to get our hands on the actual code on the syntax tree, and then we can splice the syntax tree at other positions. Let's see what example is here. Right. So x3. So I can, for example, now another quote. But now I can, if I now want to use this x2, this 1 + 1, I can splice it in here. So splicing is this $, and that's the opposite basically of quoting. So by quoting, I can get my hands on a piece of code, and splicing puts a piece of code somewhere. So if I do this and now use my pp, my pretty print for code for x3, we see the expected. So it's now the piece of code 1 + 1, the x2, times 1 + 1 again. And it's typed. So if I do something that I can't do for ints, let's say, I don't know, not or something, then I immediately get a type error. Couldn't match type bool with int. So this x2 is a piece of code, type int. When I splice it, I get an int and not expects a boolean. So I get a type error. And that's why it's called typed template Haskell. So it actually checks the types already at compile time. As we will see later in this lecture, there's also untyped template Haskell, which wouldn't make this check. But on the flip side, it's more powerful and you can do more with it. Okay, so that's that. Let's see what's next. Did I forget anything? So splice can be used to insert a piece of code into another piece of code. So it's just, I mean, if you have the syntax tree, then where you splice, basically at that point in the syntax tree, the splice is spliced in. And it's typed, so it's again type checked. Showed you this example. And I mean, it's smart. So we had this 1 plus 1. So if I just literally wrote the expression 1 plus 1 times 1 plus 1, I mean, if I just literally spliced that in, I would get something like 1 plus 1 times 1 plus 1. But that's not what I get. Actually, I get this. So I don't have to worry. I mean, it does the right thing. So it basically implicitly puts parentheses around the splices. So maybe I should say that 1 plus 1 times 1 plus 1, not. Okay. Okay. Another example. We do x. Sorry. Well, look at this. Okay. So one other thing we see is I called the variable x here, but in the actual splice, or in the actual piece of code, it has slightly renamed it to x underscore 0. So it automatically names things so that there is no name clash and other things. So, okay, so I can get sharing. So now I have to, sorry. So I don't have to evaluate, I mean, in this x3, if I look at x3 again, I mean, this would compute 1 plus 1 twice for the left-hand side and for the right-hand side. But with this x4, because I first give a name to 1 plus 1, namely x0, and then do the x0 times x0, it only computes the 1 plus 1 once, and then reuses the result for this multiplication. So the second one here is more efficient when you actually evaluate it. So we can do things like this. And we can also, I mean, it's just Haskell functions, even though it's something new. So here, so for example, we can write a function mul that takes some code representing int and generates a new code representing int. And we could define that, so it's called C, or what's it called here, X. So splice the X in, splice the X in again. Now I could, for example, do mul x2, and I would get my x3 back. So we can write functions that transform code into code. I mean, it's just Haskell functions, and this code is a type like any other type. So I can write functions where one of the arguments or several of the arguments or the result type are of this type. Okay, let's see. Okay, I showed you that basically. Okay, and for the same reason that this x3 was inefficient because we have to evaluate x2 twice, and then we did the x4. We can also do this more efficient with the same trick by first binding. So we can, for example, do let y equals spliced in x in y times y. If we now do the same as before, I mean, we get the same obviously, but with the mul prime, we now get this more efficient version where we only have to compute this expression once. Okay, did this. Okay, can also try the example 7. Look at that. 7 somehow skipped 5 and 6, but anyway. Right, and now we see it does it twice. So y1 is 1 plus 1, y0 is y1 times y1, and the result is y0 times 1, 0. So that's 1 plus 1 to the power of 4, actually. And we also see, I mean, I use this mul prime twice, and in the definition of mul prime, I called the local variable here y, but in the splice, when I evaluate this x7, it actually chooses, I mean, it calls the mul prime twice, but it chooses two different names for the y, y0 and y1. So they don't clash. I don't have to be careful to avoid name capture and things like that. So this mechanism takes care of those things automatically for me and does the right thing automatically. So this name capture is automatically avoided. Right. So now the idea is that we have this know how quotes and splices work. The idea is to use that to write basically this what we did for power 10 by hand to use template Haskell to write that for us. And there's this concept of staging. And normally we have two stages. So one stage runs at compile time, and then the second stage runs at runtime. And there can also be more than two stages, but normally it's enough to think of those two. So this transformation that we did, I'm going to look at the example again. So basically what we want to do is to create something like this at compile time. So we give it the 10, and then at compile time, it's supposed to produce this piece of code. And then at runtime, we can use this piece of code for an arbitrary x to actually evaluate it. So the idea is to do this, what we did by hand here, to write this for us, to write code for a fixed exponent for us. And now we basically have all the tools we need for this. Right, we could do this. And so this is basically a naive version. So I mean, I wrote this naive power. So let's try to do this staged. Let me just, right. Okay. So let's call that naive power prime or something. So given a fixed exponent, and I should be true to what I did earlier and use natural and integer, so we don't have to worry about overflows. And I want to get a piece of code for a function from integer to integer. Okay. So if the exponent is 0, what code do we want? Sorry, did I do that right? No, I didn't do that right. Sorry. We want it like this. Sorry. Right. So if the exponent is 0, we don't care about the base because we know the result will always be 1. And to write 1 as a piece of code, I must quote it in Oxford brackets. So that's easy. Okay. And if we don't have 1, then we just, so we have this piece of code representing x. So we splice x in. And now we can recursively, splice x in. Now we can call naive power prime recursively on n minus 1 and x, and we splice that in here. Okay, let's see. And in order to try it out, I always have my expression 2 here, the 1 plus 1. So I can do pretty print naive power. So if I have 0 and my expression 2, sorry, what was that now? Oh, prime. Sorry. Prime. Oh yeah, because this is exp int. Sorry, let me do it explicitly. And now probably I get an error here. Yeah, I must activate a template Haskell in the REPL as well. Okay. So yeah, to the 0th power, it's just 1. To the first power, is that correct? And oh yeah, sure. Second power, so it's 1 plus 1 times 1 plus 1 times 1. And third power, okay, so that seems to work. Okay, probably I should, I don't know, what do they call it here? Simple power. Okay, fine. Right, and now the idea is to do this clever algorithm, but on the template Haskell level, and that's called S power here. So natural code Q integer, code Q integer, S power. Okay, so 0 is again easy. Taking something to the 0th power, there's always 1. And now S power n is even. Okay. So in principle, it's more or less what we did here. So let y equal. Right. So I recursively call S power on n div 2, the same x. I splice the result in here in y times y. Okay, and otherwise, it was easy. It was just x times s power n minus 1 x. Make a mistake. Right. Let's see. And where do you spot my mistake? I don't see it now.
The
Oh
X
yeah.
needs to be
Yeah,
spliced.
the X. That's right. Thanks, Martina. The X nice needs to be spliced. Exactly. Okay. Right. So let's see. So if we do instead of naive power, now this S power. That is easy. For one, we also don't see much of a difference. Now it becomes, and now, for example, if we have 10. Right. I mean, it looks still a bit, I mean, it's a bit hard to read because of these qualifications here, but it's pretty close to what we wrote here by hand. I mean, it's so, yeah, I mean, it should be more or less the same, I hope. Right. And of course, it would also work for like larger things. Okay. So far so good, but of course this, I mean, okay, fine. So now we have code, but what do we actually do with it? I mean, at some point we want to actually run this code or use this code. So that's what we look at next. I just want to point out briefly that this code here is not much more complicated than my original definition. I mean, there are some splices and quotes, but it's relatively simple to write once you get a bit familiar with these splices and quotes. Okay, so now the question is how to actually use it. And the point is we can actually use these splices also on the top level of our program. But not in the same module. So if I do something like, I mean, I had this x2 here. So if I do something like x, I don't know, 8 int, now this won't work. And it says top level splices are not permitted without template Haskell. I do have template Haskell. No, I don't. Sorry, but I think this doesn't fix it. Okay, now I get this so-called stage restriction. XP is used in a top level splice. It must be imported, not defined locally. So if I want to actually use these things, I must use them in a different module. So I have a different module. So let me go to this one. I defined this use power module. So I just import the one we were working in now. And now if I load this use power here, now it actually compiles and x8 is actually 2. So I can splice these codes. I mean, I can use the splicing on the top level. I can splice it into normal Haskell code wherever I like, but not in the module where it is defined, but in a different module. So just can we maybe have a short break now for 10 minutes until quarter past?
Yeah,
And
for sure.
then show you how to use that.
Yeah.
Okay, so quarter past. Okay, I'm back. Should we continue?
Yeah, sure.
Okay, right. So what happens here now is that when this is compiled, this power module is compiled first. And now when this module is compiled, it has this splice here, and this X2 is a piece of code. So at compile time, during the compilation of this module here, this piece of code will be inserted here at this spot, as if I basically typed it by hand here. I mean, it's basically exactly the same as if I by hand typed 1 + 1 here. And I mean, sometimes one would like to know what exactly is spliced in here. And there is a way to do that. That's a flag that I can, for example, I mean, I can give it as a also in the Cabal file, so that during the compilation that is active, but I can also do it in the REPL, and that's the flag dump splices. So if I do this and reload, nothing happens because I didn't change anything, so it didn't recompile. But if I now change something here, I think if I reload, right. So if I now reload, I get this message here. So it tells me in this file, use power line 8, 10 to 13. So here, splicing expression X2. So this one. And here it shows me what is spliced at this point. So that means basically during compilation, before this use power is compiled, this text here is replaced by this text basically. And then it's compiled as usual. So this is exactly the same. I mean, in the end result is exactly the same as if I had written 1 + 1 by hand here. So I have this module that produces code, and this is then can be used in other modules. So at compile time, whatever computations I need to do in order to get my code are done at compile time, and then basically put into the source code as if I had written it by hand. So that's what meta programming basically means. Programs that write programs. Right. Right, so that's what I just showed you. Top level spice must be defined in a different module. Right. So we can tie that with our simple power. Was it called? Did I also call it simple power? I called it naive power prime. So, okay. And I should call it naive power 10 integer to integer. So I use this code I wrote here, naive power prime, which takes a natural piece of code and generates the piece of code that will then naively compute the nth power. So that's naive power prime 10. And now I need a piece of code representing this x. Okay. If I reload. Right. And I see now with what this is replaced. Just see whether it works. Right. So it still works. And we see what piece of code is put in here. So it's actually really 10 times this multiplication. And of course, I can also do that with our beta. So this S power. Reload again. Here we see what's spliced in there. So that looks, I mean, of course, the names are weird, but if we like simplify that, then we would see that it's almost exactly like this one we handcrafted in the beginning. And we can also see whether it works. So that was it S power 10 to, okay. And we can also benchmark it. Must just import the module. Okay. Let's see. So that was the built-in one. This was our original clever one, which is much slower than a built-in one. That was the handcrafted one, 34 nanoseconds. Naive one is even worse. Now, okay. So we see the handcrafted one was 35 nanoseconds, and now the one using template Haskell is 41. So it's a tiny bit slower, but I mean, insignificantly slower. So it's in the same ballpark at least. So we have reached our goal that what we did by hand here, so optimizing this clever algorithm for a specific exponent by hand, we now using this template Haskell function, we can do it automatically. And it's almost as fast. And of course, we could do it for higher exponents as well, where doing it by hand would be really tedious. And we could do it for exponent 100, for example. Change something. Right, and we see this is now the automatically generated optimized version for taking something to an exponent of 100. And of course, I mean, it's not obvious to me whether this works, but I mean, we can check with, I mean, we'll complain about types and blah, 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 but we should get the same result. Yeah. Okay, so that's an example. And I showed you the dedump splices, how you can check what is actually spliced in. Okay, I mean, on the slide it claims it's identical to the performance of the handcrafted one. I mean, our example, it was not exactly identical, it was a tiny bit slower, but I mean, in principle, more or less the same. Right, and here it claims that, I mean, because there is like, if you see this 10, I mean, here we multiply by 1, for example. And the argument made on the slides is that we don't have to worry too much about something like this because optimization is still happening. So when GHC does that, it first compiles this template Haskell, splices it in here, and then it compiles this module normally, and then optimizations that would normally happen still happen. So this ×1 will probably be still optimized away by GHC. So in the end, it shouldn't matter. Nevertheless, we saw a slight difference in performance. No idea why that is, but I mean, it's not a big one. Right. And here on the slides, we see the versions, the normal one and the template Haskell one. We see it's not very different. I mean, it's not much longer. I mean, the only thing is that we had to add some quotes and splices, basically. That's more or less the same algorithm. So if we remove the quotes and splices in this version, we would exactly get that one back. Right, and it says that sometimes one needs more significant, substantial transformations in order to get a good staged version. But I mean, in general, the idea is like this. You basically can take the original algorithm and just put quotes and splices at appropriate spots. Right. And one of the advantages, so as we saw, we can use it to generate more efficient code. So if something is known at compile time already, we spend a bit more time for compilation, but then we basically at runtime, we have this optimized version. And one nice thing about that is also, I mean, GHG is a very good optimizing compiler. So, I mean, there are literally decades of development and research on compilers and optimizations and so on have gone in there. So normally it's extremely good. It's also much more powerful than many compilers for imperative languages because due to purity, the GHG compiler can make much stronger assumptions in many cases and optimize much more aggressively. Nevertheless, it's sort of infamous for its fragility. So often, I mean, if for example, if the GHG version changes or if you make a tiny change to your code, sometimes the result, the compiled result is dramatically different. I mean, there are all these complex rules when GHG does inlining and other sorts of optimizations, and they are very unpredictable. So it's often very hard to predict what happens. I think there was some years ago, there was one of the famous packages on Hackage. I'm not sure whether, I think it was byte string or text or one of those. I mean, one of the very common ones. There was a regression that suddenly it got much worse in performance, but people first didn't notice only like after a year or so, I don't know. And that had something to do with this. So something that used to work before, some optimization, GHG optimization, suddenly didn't kick in anymore, but people didn't notice immediately. And then later they put more sophisticated tests in place that also basically check the optimized version, which is also very tricky. So even though GHG is very good in generating very efficient code, it's also very hard to predict, and it's easily, like small changes can lead to dramatic changes in the quality of the generated code. And template Haskell is one way to make that much more predictable, because you can basically by hand, write a program that tells exactly how the code should be optimized. And then you know exactly what will be spliced in there. So that's an advantage. And also, I mean, people often talk about the cost of abstraction. So, I mean, Haskell is very nice because it allows you to program on a very high level of abstraction. And some abstractions also are guaranteed to come at no runtime cost. For example, new types. I mean, that is basically part of the Haskell language specification that new types mustn't incur a runtime cost. So you can freely use them without having to worry about performance. But there are other abstractions that do come with a runtime cost. For example, I think monad transformers are quite infamous for that. So certain monad transformers can make the code much slower than as if you basically by hand didn't use them and wrote the monad by hand. And so that's of course always somewhat worrying if you worry about performance. And template Haskell is one way to get rid of that, because sometimes you can at compile time already remove that layer of abstraction. So you can still program on this high level of abstraction, but then at compile time, get rid of it. So it's guaranteed that at runtime, you won't be like slowed down by it. Right. And this is exercise. I'm not sure whether we should do that. Maybe I can just do it live. So the question is, I mean, our signature is a bit awkward, right? We have this S power. It takes a code Q integer and generates a code Q integer. And that led to the fact that when I wanted to use it, I had to do this thing here, that in order to push it in the right shape, I had to use quotes around the X. So the question is, couldn't I have had something of type code Q integer to integer? Because then I could simply splice it in, wouldn't have to worry about other things so much. So the question is more generally, what's the connection between code QA to code QB on the one hand? Is that the same as code QA to B? So, and I mean, this is not obvious, at least not to me, whether that is the same or is related or has anything to do with each other. But a good way to approach a question like that is to actually try to write functions in both directions. So whatever we call them, let's call it to and from or something. So let's just try to write a function. So we have code QA, code QB, and we want something of type code QA to B. Right. So we want code. Let's start with quotes. Right. So I want a function from A to B. So I can do lambda A goes to, well, now let me see. So I want the F, apply it to A, splice that in. Right. Okay, so that's one way to get in this direction. And now in the other direction, let's see whether we can also do that. Uh, okay, so we need something of type QB. So one code. I have my F. I can splice it in. I can splice the A in. Okay. And the question is, for example, if I do to and from or from and to, do I get where I started? And I mean, we can try it, I suppose. Let's see. Load this again. Okay, so we need something of this type here. So we, for example, we could take, I don't know, what now? Fine. And so let's do, what did I call this? PP? Yeah, PP code. Now probably I need template Haskell again. Fine. So if I have my F, okay, and the type of this is, okay, so it's code into int. So I can apply from to it, and then I can apply to it again. So I can do to from, has the same type again, and now we can do pp code of this. Right, and we see, I mean, the original, just as a reminder, sorry, let me just put it next to each other. So this was the original, it's just F, and this is to and from. And we see it's almost the same, but it's like one eta expansion. So I mean, this one, the original one is the eta reduction of this one. So it's like semantically the same. So to and from are almost inverse, but when I do a round trip, then it adds an eta conversion. But I mean, if I have this now, I could do this s power 10 here. Bit nicer maybe. So I have the s power, my s power 10. This is now, if you check here, so s power goes from natural to code q integer to code q integer. So if I plug in the 10, I have something from code q integer to code q integer, which is something I can apply to. So I can do 2 of this. So this is now of type code q integer to integer. And now I could apply that. So I could splice this in and apply x to it. And now I don't even need this. Right. So I could write it like this, which is admittedly nicer than this version here, where I need the quote. But probably it's a little bit less. Let me load it again. Use power. So if we check, so maybe let me just for a second comment out the ones I don't want right now, so that it's easier to compare. Let me reload. Right, so not sure, is it obvious which one is? Yeah, I mean, we see this eta reduction thing, I think. So this one is our original one, the one that was a bit more complicated to write. This one here, but it doesn't have a lambda, it's just this expression. Whereas this one here, the prime one, has this additional lambda here. So it's a little bit less concise. But on the other hand, it's easier to use, because we don't need to use quotes in order to actually call it. So it probably depends. I mean, one could benchmark it again and see which one is faster. I mean, we could do that actually. I have no idea whether it will be much slower. Let's see. And now come the interesting ones. 42.27. Okay, so this is like a tiny bit slower, but it's I mean, there's still a big error here, so it's not clear whether it's really slower. But yeah, so that's basically the answer here. It's sort of equivalent. I think I mean, semantically it does the same thing, but the one may be a bit less efficient than the other because of this additional eta reduction. Right. I think we skipped this one. Yeah, I don't really see the point of this. Instead, let's talk about this. So if we try this, let me just try to add that. Sorry. Range. So it's code Q int to int. Ah, okay, and now I get an error. And it's a stage error. X is bound at stage 2, but used at stage 1. So what does that mean? So stages, I briefly mentioned that before. So for example, I mean, in our main example with this more efficient power function, I explained that for splice like here or here, so first at compile time, this x2, which generates code, will be executed. And then the result of that execution, which is a piece of code, will be spliced into the source code at this point. And then this module is compiled as normally. So there are these different stages. Code is executed and then, I mean, compiled, executed, and then compiled again. And the way it works is each quote, I mean, the standard stage of Haskell program is stage 1. Each quote, or 0, I think, sorry, sure. Right, top level of a model is stage 1. And each quote increments the stage by 1, and each splice decrements it by 1. So basically out here, top level, we are at stage 1. Then we have these quotes. So inside the quote, we are at stage 2. So in particular, this X here is at stage 2. It's bound. The lambda is at stage 2. But then the splice here decrements it again. So this X here is at stage 1 again. And this is the error message. So X is bound at stage 2, but used at stage 1. So that helps us understand the error message. Why stage 2, stage 1? And right, and the problem is that basically we would need to know the value at X of X at compile time already to splice it in there, but we only have it at runtime. So, I mean, obviously the compiler can't know values during compilation that will only be known at runtime. And that's where these so-called stage restrictions come in. So everything we have done until now, it always worked out. So for example, I don't know, like Somewhat simpler. Right, I mean, for example, here. So this here is at stage 1. So inside this, so the X in particular is defined at stage 1. So inside these quotes here, we are in stage 2, but then in the splices, we are again at stage 1. So the X here and here is again stage 1, which is fine because it originally was defined at stage 1. Now, if we look at something like here, so the X is stage 1, inside here we are stage 2, but then we splice, so this is again stage 1. And the Y is stage 2, but also used at stage 2. So same stage. So that's all good. Or here, N and X is stage 1. So here we are in stage 2, but then we splice. So again, stage 1, which is fine. And here, this is also stage 1. So the N and the X, which we use in here, come from stage 1, so all good. So it was always like the quotes and the splices always compensated for each other exactly right, so that this stage restriction was not violated. Right, so far so good. So that's that. So same stage is fine. Now use at the stage before it is bound as an error. That was the strange what we just saw. So what about later stage? So if we define something as at stage 1, bind something at stage 1, but use it at stage 2. So for example, let's try this. So this here doesn't compile, that's a stage error. Try this persist. We take an int and produce a code int. Right, and now if we look here, so n, I mean, this is outside the stage 1, inside the stage, the quote, we are at stage 2. So this n is actually used at stage 2, but defined at stage 1. And we don't get an error. And if we think about that, I mean, what does that mean? We have this, I mean, we must basically, for a given int, we must be able to produce code representing that int. And if you think about that, that's sort of like serialization. So we have an integer like 42. And in here, I mean, to produce a piece of code, we have to now produce a piece of code that represents the integer 42. So like in normal Haskell code, that would be the string consisting of the 2 digits 4 and 2. So this is similar to serialization. And that actually works. I mean, we can try this out. Look at PP code, for example, persist 42. And we see, I mean, it's indeed this, I mean, or we can also use this, what was it, show code? Right. So here we see it a bit more clearly. So the 42 is basically converted into code, like an integer literal representing 42. So this works. So so we need somehow to convert this int into a piece of code of type int. And for int, this is simple because that's just a literal. Sorry. So we can try this example as well. So if we do persist 1 plus 1, for example. So that's 3 times 2. It's not 3 times 1 plus 1. So the 1 plus 1 is, I mean, that here it's an int. It's not code int, right? The n is an int. So if we do 1 plus 1, it actually gets evaluated to 2 and then represented as code here. So this is different to what we did earlier with this expression 2, where we actually have the 1 plus 1. So here the 1 plus 1 is actually an int, And then we sort of serialize 1 plus 1 as a piece of code, which is the literal 2. And so you can do that for ints, and you can also do it for other types, but not for every type. And there's a type class for that, and that's called lift. So we can, I'm not sure whether that's in scope. Of course not. Let me just, I will get the correct error message. So this won't work. If I do it for arbitrary type, but now the error message will tell me what I need to import. Okay, language Haskell, template Haskell, syntax. It was the one I had earlier, and then I removed it. Okay, so that's where this lift class is defined. So now that should compile again. And now I can also use it for whatever 42.0 type double. Sorry, PP code. Right. And if we ask for information on lift, we see in particular it has this lift type. We can ignore this quote M constraint for a second. So it takes our type T and turns it into MX. And we haven't talked about X yet, but code Q is actually right. It's a synonym for code Q. If we ask for code, this is a new type wrapper around TX. So this is the underlying template Haskell, a typed template Haskell expression of type A. So yes, so lift allows us to basically turn a value into a piece of syntax. That's what this says. Oh yeah, and here we have this lift typed, which is exactly this. So code Q, what we have been using for now is basically a special case that this monad M here is Q, so-called quotation monad, where template Haskell happens. So basically that's it. So taking something of value T and turning it into code representing something of value T. And the good news is you don't have to do that by hand. There's also an extension to derive liftable, basically, to do that automatically for your custom data types. And it works for most types, but not for something like function types, for example. But we also see that it is already defined for like all the common types. So like the numeric types like words and naturals and so on, but also for pairs and either and Booleans characters, I assume also, maybe, probably also for lists, I suppose. Not sure, should be. Don't see the instance now, but here. Right. So for most types, it's anyway already defined. And yes, you can also automatically derive it. So for example, we could do again our standard tree example. What was it? Leave A or node tree A. And we can also say lift. And then I just need the derive lift extension here. And then that okay, so then that works. And now, for example, I could do, I don't know, I have a sample tree. Oh, no, T2. Okay, and now I can lift code it. And if I then print code, or I can persist, whatever, persist, x3 should work. And there's no show instance, but now I should be able to use my, right. And this is basically, I mean, more or less the same that's written here, but now just with qualified names for, I mean, power.node, power.leaf, ghg.types. So this is the piece of code that represents that tree. So as you see, it also works for custom data types. Right. So lift class. And as I said, it's a form of serialization. So it's a little bit like the show class. You can do it automatically for most types, but function types or IO or something like that is not an instance of lift. And right, we can also do that explicitly, I think. Although I mean, this just didn't work right now. I tried it, but it should work. I'm just a bit confused why this PP code didn't work. Because it didn't work. Oh, it does work. Okay. So that means something like this here, where we had this stage difference, because I mean, this was defined at stage 1 and this n is at stage 2. So this works because there is an implicit lift going on here to lift it from stage 1 into stage 2. So we could alternatively also write it, or explicitly write it like this: lift typed n, and then splice that in. And now the stages match precisely. So outside is stage 1, inside the quote is stage 2, but inside the splice is then stage 1 again. So n is bound at stage 1 and used at stage 1. And then it's lifted to quote. This quote is spliced in here and then multiplied by 3. And this also works because that does this here implicitly. So the quoting mechanism implicitly adds lift typed where necessary to lift it into the correct stage. Right. So that's that. Okay, and we could write one by hand. So let's. So if we didn't derive this here, could write it by hand. Okay. Instance lift tree, and I assume we need an instance for A. Okay. So that's just a normal function now. So lift typed. So we need to lift a leaf to code. Well, I mean, it's obvious what we write here. We need the leaf constructor, obviously, and now we need code for X, which is of type A, and I said A is liftable. So I mean, I could just write this, or I could X, because of this implicit verb, but I mean, I can do the same that I did here to make it more implicit, and write lift typed X. Right, and for node typed node left right. So that would be node left typed left typed And that should work exactly the same as before. So if I now do this, yeah, I get exactly what I did before. So this is exactly what the automatic deriving also does. So there's no, I mean, it's no magic. Right. Okay. Okay. Okay, and this is that in every splice we can use top level definitions. So they work in every stage. So something that's like globally defined, I mean, defined at the top level, we can use everywhere. So I don't know if I had some foo. Uh, Something like this, I would be able to use foo in arbitrary splices. So I could do a um, string. That would work, I think. Right. So so this foo, because it's defined on the top level, I can use it everywhere in every stage. I mean, this is bound at stage 1, but I use it at stage. I mean, I use the foo function at stage 2 here inside a quote, but that's fine because foo is a top level definition. Right. Okay, and this is actually an interesting exercise, but I'm not sure whether you should try that or whether we should do it together. So maybe we can do this exercise together, and then we can have another break. And then after the break, we can get a bit more practical. I mean, this is basically, yeah, right. After the break, we talk briefly about untyped template Haskell and quasi quotations and how to actually, I mean, how in the wild, like for lenses, one actually uses it. So even if you don't have to write these quotes yourself. So this idea of the memoization functions, I mean, often you have a function that, I mean, probably a lot of you have heard about something like dynamic programming or so on. So sometimes you have functions where that are very slow to compute, but they become fast if you remember results of previous computations. It's especially true for like highly recursive functions. And then it can help to basically remember the result of the same function called on smaller arguments, for example, if it's like numeric arguments. It's often runs under the heading dynamic programming. And in Haskell, there are actually very nice ways to do that without template Haskell, but that's a different story. So the idea here is you basically get a list of function arguments and a function, and again, the same function. So this is a hack that's explained here. I come to that in a second. So just think a list of arguments and a function, and you're supposed to produce like code for the same function. But now, if the argument given to the function is one of the ones in this list, it should like memorize them. So let me give you an example first. And I think we will also do it more general because all these ints are confusing, I find. So let's look at something like Fibonacci. I mean, that's like the 101 example for recursive functions. And let's also do it with naturals because I find that's better. And let's do it completely naively. So the definition of the Fibonacci function is if it's 0, it's 1. If it's 1, it's 1. And if it's something larger, then it recursively calls the Fibonacci function at n-2 and n-1. I mean, that's a beautiful definition. A nice example of a recursive function. It's actually double recursive, but it's also, I mean, as far as efficiency is concerned, it's horrible. We can try it. 0, 1, 2, that's all good. And we can also do fib n, let's say from 0 to 20. What did I do now? Yes, I know. Right, I mean, nice. But if I do something like fib 25, it's already notable. I mean, it takes. And I think something like fib 40, I will probably wait forever, very long. Right. So now the idea is, if I could, I mean, because of the way it works, I mean, the small arguments, I need over and over and over to look them up again. So the idea is if I, this memoization idea, if I did it by hand, so manual, to do something like this. Let me think. Hang on. So basically we have this memo table where I just remember some small values. Let's say 0, 1, 1, 1, 2, 2, 3, 3. It's boring. So now it's 4, 5, 5, 8. Something like this. And then basically use this table for the values from 0 to 5. So case, sorry. Not sure whether we ever used the find function before. Just a second. So that's one of the functions in the base library. It works for arbitrary foldables, but in particular for lists. So it gets a list or another container and a predicate. And if it finds an element in the container that satisfies the predicate, it returns it, just that element, otherwise nothing. So we can do, for example, find even 1, 1, 3, 10, 15, 20. It will give me the first element that satisfies the predicate, that's even in this case, which is the 10. And if there's none, then it returns nothing. So using such a memo table, what I could, for example, do is, so I use case find. So I have these pairs, and I check whether the first component of the pair is the argument I'm looking for. Table of, so if I find it in my memo table, the result is X. And if, sorry, result is X. And if not, then I recursively do fib manual and -2 plus fib manual -1. Okay. And let's see. First of all, whether it works. Yes, and now it could also be a bit faster than the earlier one. although probably not fast enough. Let's at least try. 30 is faster. Yeah, not really sure whether it's faster than before. Yeah, I think it is faster actually. So there was a notable difference, I think, right? Does anybody remember how the timing? I always forget.
S, was it? The flag?
Yeah, I think so, but plus, I always forget. Plus S, yeah, you're right. It's just plus was my stupidity. So the normal one, the normal fib with 30 takes 1.91 seconds, and the one with this little memo table, it's almost twice as fast. Right, so the idea is to do this. I mean, I did this manually, right? So I created this table and then wrote this. So the idea is to use template Haskell for that, for an arbitrary function, more or less. So let's try this. So smemo, so it gets, and I want to challenge, so I don't just do it for int to int, I do it for arbitrary a's and b's. Let's see. So we get a list of arguments that would be in our example 0, 1, 2, 3, 4, 5. And I get a function from a to b. And I get the same function again as code. The reason I need it twice is because functions are not liftable. So if I just have the function, I can't get, in general, it's not obvious how to get the code of the function. So this is this hack. But we will see in practice it's easy to use. And I basically create code for function of the same type. So the idea is I give it something. I mean, actually, I could already implement this. Use it so that we can see how to use it. So the idea would be I do something like memo fib from natural to natural. And memo, why is it? Okay. So I use my smemo. For 0 to 5, and the function is fib, and the code of the function is also fib, and I splice that in here. Just natural must be in scope. And what's the problem there? Okay, fine. Now it can't splice it in because it runs it at compile time, and I get this error that's undefined. But that's how I would use it. So the idea would be this memo fib would be basically the same as this thing, this fib manual. But I don't have to like write this logic with the find and everything by hand. Right. I mean, this is one way to do it. One could also, anyway, let's try this. So how would I do that? I mean, I must basically generate this code somehow by hand. Yeah, I mean, what I did by hand here, I must now put that into code so that it works in general for general functions. So let's call it, I don't know, access and F and C for code. So first of all, I can again compute my table. I mean, I do that, of course, at compile time. I want to compute this memo table once and for all. So that's x comma y, where x is from xs and y is fx. So this is my memo table. And now, I mean, I basically just write more or less the same I did there, I hope. Okay, so sorry, it's so given an x. So case find p first p equals x. And here I see I probably need an e constraint on a. but hopefully the compiler will let me know this. Access. Right, and so somehow I must splice that in. So I probably need some sort of lift constraint there. Sorry, table. So I need something like lift code table. Of. Let me see whether multi-lines should also work for these, right? Yeah. I get all sorts of errors. Okay, fine. So if it's just comma y, it's y. If it's nothing, well, then I must use the actual code that I got. I think it won't be just as cool as here. But anyway, let me first do it. So so I splice the code in and apply it to X. Now I get all sorts of errors. Let's see. Um, what did I want to write here? C. Anybody understand this? Obviously, I'm in the wrong monad somehow. Scope type variables. Yeah. And this I don't need because I have template Haskell. Okay. Somehow it's complaining that I confused the list monad with the queue monad. So somewhere I must do something horrible. Let's remove this quickly. Okay, yeah, this looks better. Anyway, right. Okay, so now I think those errors make sense. Right, so obviously I need equality for the find to work. Equality on A, so that's clear, that's good. And in order to splice that in here, I also need that A is liftable. Not sure why I don't need that B is liftable, but let's see. Maybe I also need that. Eq A, lift A. Right now I probably, yes. Okay, right. Looking good. And now if I go back here, now the error is also gone. Let me just change something and reload so that we see what's spliced in. Why not? Oh, probably I closed the REPL in between, so I must set this tdump splices again. Sorry. Right, there we go. So let's see. Okay, and here we see the code that's spliced in. Let me just go back to the definition here. So this looks like quite close to what I wrote manually. So we see, for example, this table. So it's been computed at compile time, and this memo table here that's now been spliced in is exactly the one I computed here by hand. And this is also all relatively nice. The only problem is here I'm using the original function now, which is not good. I mean, ideally I would like only do one step of the original function. Here I did it better. I mean, here I'm using basically again the fib manual, so I make it recursive, and here not. So once it doesn't find, so this will only be fast for like the first 5 values, but then as soon as the argument is 10, for example, because it doesn't find it in the table, it will fall back to the original fib function. And then even when it gets to the small arguments, it won't use the memo table. So if I wanted to fix that, I could fix it, but that's a bit awkward then. Could do something like, sorry, if I copy the definition here of the fib function, paste it in here. I think that would work. Just give me 1 second. If I do fib prime, so it's exactly the same. But now here in the recursive call, instead I use memo fib. And here I use fib prime. And fib prime, that doesn't work by... okay. Yeah, so I can't do it like this. So this is not as good, actually. So I can remove this again. I mean, this will work. I can try memo fib for but as soon as I do something like this, then it will be slow again, because it won't, once it gets to small numbers in the recursive calls, it won't look at the table. So it will only be fast if it's actually in the table. Of course, I mean, the plus is I could do something like 50 here, or 40, let's say 30. And now compilation takes a long time, because now in order to compile it, it computes this memo table by hand up till 30. So now it uses this table. So now all values up till 30 should be like instantaneously, basically. But as soon as I use one that's not in the table, it will be slow again, because it will fall back to the original definition. But I mean, it's not an exercise in dynamic programming, it's an exercise in template Haskell. So this is actually, I think, quite a nice example, because you see that, I mean, compilation took a really long time. Of course, now during compilation, it was first computing this memo table, which took long. But then it splices it into the code. And so now at runtime, as long as our value is one of those 31 values, it's almost instantaneous that it gives the value. And I mean, we don't have to do that by hand. I mean, all we say is what values we want in our memo table, and that's that. Of course, I mean, this is like horribly complicated. I mean, just as a side note, this is like terrible to write Fibonacci like this. I mean, there are many. I mean, I think there's a website actually, like 500 ways of writing Fibonacci function in Haskell. And let me just, I mean, for example, I mean, a clever one, just, I mean, like proper fib. Would be this is actually a good one. So the list of all Fibonacci, the infinite list of all Fibonacci numbers is just 1 and 1, and then zip width plus drop 1 fibs, drop 2 fibs. And once I have that, I can just say it's fibs. Right. And I think this is okay, fine. From integral. It's from integral, of course. Sorry. No. Is that the one? Oh yeah, it takes so long now because it's computing this memo table again. But now I should have it. So proper fib. Hmm. I thought that was so fast. Did I make a mistake there? Obviously.
Mm.
Sorry, it's a bit embarrassing because this is one. Just put that to top level.
Ah, no.
Let me just make this here smaller again, otherwise compilation always takes so long. Okay. Hmm. I think it's this is wrong. Like this. Yeah. Right. Ta-da, now should be fast. Yes. And now I can be really ambitious. Yes. So that's like an efficient way to do it in Haskell, which is very cool, I think. I mean, this definition, for example. So, I mean, we don't have to, I mean, this is a silly example. I mean, nobody should use the naive definition of Fibonacci numbers. This double recursion is horrible for performance. And this is a much more elegant and faster way to compute it. So I can, without any problem, compute the 10,000th Fibonacci number. And of course, in the specific case of Fibonacci, there is even constant time, basically, because there's a closed formula to get the end value. But anyway, that's besides the point. I mean, this was about, or is about template Haskell. Right. So that's that. So that's this exercise, this memo stuff. And I think the next topic is untyped template Haskell. So we should have another break, I think. And then we can briefly talk about that. That's right. And then, as I said, quasi quotes, which is very cool. And then just in the last half hours or so look at some examples like out there on Hackage to actually use template Haskell, which is also nice, like lenses, for example. Let's have a break until 40, maybe.
Okay, sure.
Okay. Okay. Okay.
Okay.
Right. So right now, I mean, until now we have talked about typed template Haskell. And one of the things, I mean, these quotes that we use, they were always expressions of a specific type, for example, of type int. But sometimes we want to generate code where either it's not so obvious what the type should be, or even it shouldn't be expressions. I mean, for example, as I said before, for lenses, there is a way that I will show you later how to actually generate code for lenses automatically. And if you, I mean, then we need like these lenses, which are top level definitions of a lens. So it's not just an expression, it's a top level definition. And that is something we can't do with type template Haskell, but we can do it with untyped template Haskell. So with untyped template Haskell, you can generate arbitrary code, including top level definitions or definitions of types or classes or anything you want. So in particular, I mean, declarations or types or patterns. And for that, there is untyped versions of codes and splices. And that's actually, as I said in the beginning, older than the typed version. So that's from 2002, it was it? Whereas the typed stuff only came 2012 or so. So, I mean, we had this very first example, and then this type template Haskell, which was represents an expression of type integer or int. And we also have, and I showed you this code Q is actually a type synonym for code Q, and code is a new type wrapper around QX. And so we can also do this. So let's try this. So x2 prime of type QX. X2 prime. Reload. Right, that also compiles now node. It's only one vertical bar. So that's what's normally called Oxford bracket with one vertical bar, and that's for untyped template Haskell. And what was this? X3 was, okay, this thing times itself. So we can also do this. And now a splice, an untyped splice is just $1 sign. Okay, so one vertical bar less, $1 instead of $2. So that's for the untyped version. And so I mean, if it's an expression, it always has this type QX. And here we can also build stuff that is actually not type correct. And that won't be caught at this point. So what's it called here? Whatever. Why? No idea what TE is supposed to be. We could write something like head true. And that would compile just fine. But if we try to use it, use T, So if we splice this in, then we get the error message that we would expect. So it tries to splice that in. And then, I mean, as I said, how it works is the template Haskell is evaluated at compile time. And the result, if the result is a Q expression, like a piece of code, it's spliced into the use side, in this case here in line 36. So this is now as if I had written by hand here, head true. And then it's compiled. And then the type checker, the compiler, catches this error that, I mean, you can't take head of Boolean because head expects a list. So it's still fine. I mean, we still can't make a mistake. I mean, we still can't write invalid Haskell. But it gets caught only when I splice it, not when I define it. Whereas if I use this, I mean, if I showed that before this, but if I try it again, so if I try to do the same thing, I can't even know, I don't even know what type I should give it here, but let's try it without a type. So if I try this typed version, then I get the error here already at the definition side of this. So this is immediately not a valid typed expression. But this is a valid expression. So, I mean, the error gets caught in any case, but when I use type template Haskell, it gets caught earlier already when I write this invalid expression. Whereas in the untyped case, it only gets caught when I try to use it, when I try to splice it into code. So in that sense, untyped template Haskell is less safe. I mean, in the end, when I want to use it, it's still type checked. But when I define it, so I can come up with nonsense expressions, basically. Right. So that's that. That doesn't, of course, show us why it would be useful, but just to demonstrate the difference. And I showed you the splices. And staging works exactly the same as before. And now we see why untyped template Haskell is like more powerful than type template Haskell. So again, if we can use type template Haskell, we should, because errors get called earlier, so we can't even write like expressions that don't type check. However, if we want to go beyond expressions, then sometimes we have to reach for untyped template Haskell. And there we can not just do expressions, we can also do, for example, patterns, declarations, types. So we can do something like this here. So this is a pattern. This is a declaration. We define a function foo. This is a type. And so the quotes is again these Oxford brackets, but now with this letter between the bracket and the vertical bar. P for pattern, D for declaration, T for type. And I think the one we have used until now without a letter is just actually an abbreviation. We could also write an E for expression, I believe, if I'm not mistaken. I think this is the same as writing E here. Or maybe, yeah, okay. So this is just because it's the most common case, you can leave the E out. Okay. And let me see whether there's an example here. Right. So splices can everywhere where they are expected. And declaration splices are only allowed at the top level. So maybe, I'm not sure whether there's an example here. Right. So I think there is an example later in the slides, otherwise I'll give you one. Sometimes what we have done so far is not sufficient for what we want to do. So the standard example for that is tuples of flexible size. And for that, we can actually use like Haskell abstract syntax directly. So not using a quote to get our expressions, but building it directly. I had this show function that I used a couple of times. So for example, this show code x3, for example. So this I mean, of course, we always didn't write it like that. I mean, we defined our expression 3 nicely like this as a quote, but we could also do it explicitly like this. So build the syntax tree explicitly. It's much more verbose, but it gives us greater flexibility because we can build this programmatically, something that we can't write down as a quote. And there's, I think, I mean, this is on the slides, but I should actually show it to you. So if we go to template Haskell on Hackage, this library we have been using, I think it's, I'm not sure why it is. Okay. Probably in syntax. Sorry. Stuff. Right.
You can control F if you want to.
Yeah, right, it's in the syntax model. So basically everything that we can write in a Haskell source code file. I mean, the whole syntax, everything, expressions, patterns, type definitions, everything basically is made explicit here. So here it's types, even module stuff, extensions, fixity declarations. And then there was this pattern thing that I was looking at now. This here. So patterns, for example, all ways to have a pattern. Right, I think I should give an example here. I mean, and that's just like the 101 of untyped template Haskell or a variation of that. So I mean, we have, if you recall, we have first and second. So we have first, for example, which takes a pair and gives us the first component of the pair. And but there is no such thing for triples, for example, or quadruples. So if we want the first element of a triple, so we have to define it by hand. So for example, like so. Okay, and then we can do it for whatever Haskell true 42.0, which gives me the first component. But that is not in the standard library. So in the standard libraries, we have this first FST only for pairs. And one standard example of template Haskell is if we don't want to write these things for more tuples by hand, but instead do it like for all of them. So the idea is to write something right. Several ways to do this, but just try to think about the name. Don't want to complicate things. So for example, co-expression. So first, let's call it, I don't know, my first. So which takes like an int for the number of elements in the tuple and gives me a Q expression. My first n. Right. And okay, and this is, I mean, we can do this now, but maybe we should first, I think with template Haskell, it's always a good idea to have an example. So we want to do something like this. So I don't know, example for 3 or something. So I want to generate something like this. So what I did in the REPL. So I want to, let's say for 4. So what I want is something like this. Okay. Why is that? Ugh. Okay, fine. I think this show code now doesn't work because I must just use this. Sorry, I need just a variation of this here. Exp. I think it's just as simple as this. No, it's not. Q expressions are not showable. Does the p print work? Just give me 1 second. I think there is a way to show them. 1 second. Should be. So this is this expressions. Well, there is a show. So I don't know what the problem is. Shouldn't I just be able to do print E? Sorry. I need to. Okay, fine. Now I know. Right. Okay, fine. Sorry about that. Right. So this should work. So now I can show these as well. So for example, this TE, this nonsensical one, I mean, it's a perfectly valid expression. It's just, I mean, it's not type correct Haskell, but as an expression, as an untyped expression, it's fine. And I can show it now. And I can also do my X3 now. X3. Right. So here we see what I want. I want to basically build such an expression. So it's a lambda, and the lambda expression takes this list of arguments. And in my case, the argument is this pattern here. So it's a tuple, tup-p, so a tuple pattern. And then this tup-p constructor takes a list of patterns. And I name the first one. I name it X. So this is this var p, var pattern, variable pattern with a name. And then wild p stands for wildcard. So these underscores are wild p's. And then the body of the lambda is a variable expression, and the name is the same as that one. Right. So so that's the idea. So now the only question is, how do I get a name? So if I ask for the type of var p, for example, it takes a name. So I somehow must get a name. And the whole thing, this Q is a monad. So if I want to do, so first of all, I must find out how to do a name. And I I mean, that's the whole point of this Q monad in which all of template Haskell happens. Let me just go back to the top level. Because I think that's explained right at the beginning. If I look here, names, constructing names. Okay, so there's a make name function. That's easy enough. Okay, fine. I suppose I could also just use splices, whatever. So the point is something like this. I can't do with quote if the length is variable. I mean, I want to do it for arbitrary here. So, right. Let's first do undefined. So I mean, I want to create this thing here, for example. So do this. So pattern p secure pet. So what do I want to do? I want this var p x at the beginning. So it's a var p. So als name, I could use this make name, but I think I can also use a pattern. I'm not sure whether this works. No. Okay, fine. No, let me do it by hand. So I use this make name X. Okay, fine. This is a pattern. Okay, and now I need these wild p's here. So replicate one less than my tuple size, wild p. Okay, now I have a list of patterns. Fine. That's okay. Right. And now I want to, if I want a pattern, so I must apply the tab p constructor to this. So I can get a pattern. I can do tab p. Right. So now I have this thing. And now I should be able to actually write this. So it's Oxford brackets. Or maybe not, because I mean, the name must be the same. So let me do it in the Q monad. So let x equal make name x. Right. At Okay, so far so good. And now I should hopefully be able to, no, maybe not. So I can just lam e sorry, just 1 second. So I think this is wrong. This make name is wrong. Right, I need a new name. Make name, it could actually capture something. Right, sorry about that. So, because I mean, if something is called X in my program, I don't want to use X, I want to use a fresh variable. So this is this. Okay, fine. Okay, and now I can basically just copy this here, I think. So lambda, now the pattern I created, the P, and now var ex.
Missing
Get.
the let.
Why is this not working? Ah, because the right. It could have lambda can have more than one variable. Okay, so now that should work. So my first, and now I can do stuff like I mean show x my first 4. This is what I had. And now it picked the name x1 actually. I could also do now for 10 tuples and would get this. And now I could actually right. And if I actually wanted a declaration, so if I want to, I mean, use this and give this a name, so I could do something like instead of expression, do it. Sorry. Not actually sure how declarations work. Let's see. So let's look for deck. So if I now actually want to really define a function, okay, so here that's, I think okay, so there are 2. Okay, I mean, I can actually do it like this. I don't need a lambda, so I could also do this. So function, name of the function, and then a list of clauses. I mean, what I want to do, sorry, so what, I mean, this was already okay, but I mean, what I actually want to do is something like, I want to define functions, let's say first underscore 4, which takes a quadruple, like this. So something like that I want to generate with template Haskell. And then like for 5. And then it's this. But I don't want to write these things by hand. I want to automatically generate them. I mean, I'm always almost there. I already have this lambda, but now I want to actually generate a top level definition for it. So so I instead of qx, I can do q deck, list of declarations. I think it always has to be a list if I want to splice it in. In this case, I will only splice in 1. Right, so I again pick a new name, but I also the name of my function. So there I use the make name because I want a fixed value for that, and I call it like first underscore show n, for example. Right, and now I can use this. Let's see. So I need this fund d. So pure fund d function name. Okay, and now as clause, what's a clause? It has a list of, okay, it has the clause constructor. So it's clause in a list of patterns. That's what I already had. That's my P. And then the body, and the body is just my var ex. And why does that not work? Let's see. And then it's a list. This is where clauses. So these declarations are where clauses, but I don't have any. Now why is this not working? Because body is something else. So let's see what body is. Okay, it can be guarded to get something like this or normal. So in my case, it's normal. Okay, this actually looks good. And now I should hopefully be able to use that. So my first, so let's see. So the way you would use it is like this. My first, for example, 4. Right. And now I just get the warning that I don't have a type signature. But if I now load this use power again, I should see what's spliced in here. So I see now at this point, now I have this first 4 definition exactly like I wanted. I mean, with weird name for the variable, but it works. And I mean, I could do 5, 6, 7, 8. And if I reload, then all of them should be spliced in here. So I see that all these definitions are now available. Now I can do something like my first, sorry, now they are called first underscore, for example, 5. And now I can do X, Y, Z, true, false. And I get the X. So now this first 5 is actually in scope and defined. So I have spliced it as a top level in here. And of course, I could also even do it. I mean, now I can get crazy and do things like my first. Okay, and now I could even do this cooler and do something, replace all of this with my first 4 to 20. And now I have defined functions first underscore 4 until first underscore 20. So for example, first underscore 19 is now in scope, and it should take a 19 tuple and extract the first element. Right, and of course I get this annoying warning, but it would also be possible with template Haskell to actually add a signature for this, a correct signature, so that the warning gets away. But we see it's really exactly the same effect as if I had written this by hand into the code there. And if by hand I leave out the signature, I would get exactly the same warning. So I think if you did this professionally, like for proper library, one should probably add the type signature as well, because then it's a bit more work. And we see it's relatively, I mean, I also always have to look it up. I mean, these how to actually build that. But I also do it like I showed you now. I mean, I do an example and look what it looks like. And then these things you just find with the documentation, what you need there to actually assemble this syntax tree. Right, so that would be an example of using untyped template Haskell to actually splice actual definitions of top level, in this case, functions into a module. So now with this one line of code, I have defined 17 functions and that extract the first element from a tuple of length 4 to 20. Right, and I get all these warnings. Okay, let's see what's on the slides. I think I was a bit slow. I should speed up a bit. Right, okay, fine. So, I mean, we saw there are all these constructors to do basically everything you can do syntactically in a Haskell file, in a module, you can also do explicitly with these constructors. So we saw how to do declarations and patterns, and for everything you can think of, even for like extensions and things like that, and where clauses, let bindings, all these things you can build them explicitly using these types. And this Q monad, I mean, I only briefly mentioned that. So basically these template Haskell thing computations, sorry, if I go back here, they happen in this Q monad. And in principle, you can think of the Q monad as IO plus a source for fresh names. So often when you generate code, you need fresh names because you don't want name clashes with existing names. So this is basically the point or the main point of this Q monad, that it has this new name function which generates fresh names for you that you can then use in your code. But it can also do IO as, I mean, I had these somewhere. I had these helper functions. Where are they now? Gone. This show stuff. Please tell me I didn't delete that.
At the
Cancel.
bottom,
It
or
was at the bottom.
maybe in the use, you're in power, in the use power at the bottom, or in the
I
main.
think I accidentally deleted it
Oh,
here somewhere. Hmm. Yeah, I try to.
mm,
I think it doesn't matter. I mean, right, but anyway, so you can also, it's a monad IO. So with using lift IO, I mean, maybe I can write this show expression thing again. Show X. So that's in, if I want something in IO, show X E2. So now I'm in the Q monad. These expressions is Q express. So to get to the actual expression, I must like bind to it. And then I can do, because it's a monad IO, I can do lift IO and then, for example, print X. That was, I think, what I did, wasn't it? Why does that not work? Did it work earlier?
because of the
Ah,
type.
yeah. Sorry, it's right. And now, oh yeah. Oh yeah, sorry, and it's run Q. So to actually lift it in IO, you must do run Q like this. Okay. So I mean, this is in the Q monad, and then with run Q, you can actually run it in IO. So I bind to this expression, and then it has a show instance, so I can, and in Q I have lift IO to execute IO actions. And so yeah, the main point of this Q monad is this name stuff, this new name. I think that's the main point. Why you need like a special monad and can't just use IO. We can think of Q like IO plus a source for fresh names. And so in particular, you have lift IO. And that means you can do arbitrary IO at compile time, which is also controversial. Because in principle, I mean, if you use somebody's template Haskell code, I mean, you should make sure that you trust that person because he can do arbitrary IO at compile time. So when you compile it, when you splice it in somewhere, then this is executed and it could in principle wipe your hard drive or something. But of course, I mean, it's meant to be used. So for example, it can go on the net and check something at compile time, or it can read from a file. So one common use of template Haskell is also, I mean, you could have some like configuration files or whatever, and then at compile time, it would read the configuration file and use the information in there to do whatever, to generate some code. I mean, maybe you have a configuration file and you want like values from that configuration file, like hard coded into your code as global variables or something. And you could do that with template Haskell. So it's very powerful, but also a bit fishy, or maybe too powerful. So that's this stuff with this Q type, and there are all these synonyms. So we worked with Q expressions, and then I mean, there's a type synonym for that. So XQ or Q pattern is PETQ. And there are all these things. Sorry. Okay, this is just another example. but mine is nicer, I think. Sorry. Right. And YQ, I already said, so that it's a monad. The main point is that it generates fresh names for you. And it allows you to reify information about existing Haskell entities. So that we haven't seen yet. So right, so there's this function. So given the name of some existing Haskell object, you can get in the QMonad information about it. So maybe we can try that out. I hope this info type is showable. I assume it is. Let's see. Yes. So let's write another function here. Show name info. So given a name, so we get the info with reify, and then we just show this. Right, and this is now a third. So we learned about the quotes, these Oxford brackets, about the dollar or dollar to splice, and there's a third thing, apostrophes or single quotes or double quotes to get names of things. So for example, if I now reload, now I can use this show name info. So for example, if I want information on X2, so then I should, okay. Okay, fine. Okay, so that doesn't work. This is a bit silly. Okay, so I can't demonstrate that. But the point is, so we, it's a bit weird, isn't it? Does
Yeah,
that work for?
maybe GHCI, but if you run it as a binary works.
Yes, that could be the case. What's with types? Also not. Ugh. Yeah, probably if I do it as a binary, that should work. Okay, fine. If I do okay, fine, not IO. Let's do a Q expression. Um, let's do a code Q string. Let's try that. Uh, hmm. Uh, okay. Okay, that works. Let's see whether that works. So if I now splice that in somewhere, so I basically get the information of a name, show it, and use that as a string. Not sure. Let's see. Whatever. Pips info. Okay. Why? Okay, that actually seems to work. Okay, it's a bit backwards, but okay, fine. So I can, okay. So there it is, my information about fibs. And what was it? It was a list of naturals. Okay. So so this tells me, I mean, this is now in this info type. So it tells me it's a value. And it gives me the name, which is used, the qualified name used power fibs. And it tells me the type, which is the list constructor applied to the naturals. So, and whatever. So that means this gives me the information. So in the Q monad that this fibs thing is a variable of type list of naturals. So the whole point is, and I mean, I could do, so for values, you use one apostrophe, and for types, so for example, int info, or let's say tree info. So you use two apostrophes. So we had our tree type. So if I do this again, so now I can ask for tree info. Okay. And it gives me all sorts of information. So it's a type constructor, whatever. It's called tree, probably somewhere. I mean, all sorts of strictness annotations and whatnot. Right. And then somehow it's also possible to get to the constructors and so on. I'm sure. Yeah, here's this node thing. Here's the leaf thing. So it tells me it has a constructor leaf, it has a constructor node, and it tells me also the arguments. So the leaf constructor has this vati a argument, which is which we see here. That's basically, it tells me tree is a type that's parameterized by one over one type variable of kind star, and this is named A756 whatever here. And then it has the constructor leaf, which takes such an A, and it has the constructor node, which takes again a tree A and another tree A. So the point is, in the Q monad, I can inspect Haskell values or Haskell types. So for example, and this is then how for example, derivation for lenses works. So probably this is now the time where we should demonstrate that actually. So let me briefly, quickly import lens. Okay. Okay, so let's say I have a type, a very simple type, whatever, person. Person, name, string, age, int. Doesn't matter. Okay, and now I want to write lenses for this. And I mean, until now we did that by hand, but I also told you that you never have to because you can automatically derive that. You must just check what it's called. I think make lenses or something. And traditionally, if a library has template Haskell support, those modules are always have something like capital T, capital H in their name, like this one. So this control lens.th is the template Haskell for support. And we see there is something make lenses. It takes a name, and dex q is a synonym for queue of list of declarations, same as what I did for my firsts. So that tells us we can splice that in with a name somewhere. So here's an example. So I can now do if I import it, of course. Control lens, yes, th. Make lenses. I think I must reload. Right, and now I can do make just like this. Just on the top level, I write make lenses. And now I must give the name for what. So in this case, it's for the person type. That's a type. So in order to get its name, I must do 2 single quotes, not to be confused with a double quote. And if I do that and REPL and load use power, and set means dump splices and again and reload. Then, I mean, this is all my stuff. Here. So this is now comes now from the lens library. So make lenses. So this line results in these the splices. So it defines something called age for me and something called name. So age is a lens from person to int. Name is a lens from person to string. So without having to do this boilerplate by hand, I immediately get it now. There's one caveat. Normally, you can do recursive definitions. Hang on. So for example, you can do something like data address, country, string, city, right? And I could have something like address here. And now to our horror, this doesn't work. And we see not in scope. The reason is when you do a splice like that, normally in Haskell, it doesn't matter in which order you declare things. You can use something like address before you actually write it in the module. But when you do template Haskell splices, that doesn't work. So basically the splice is like a cut in your source code file. So it can only use anything above this line. So, but it's easy to fix normally. I mean, you just move it so that everything you need is there. And then you could also do make lenses address. And now if we reload, we should have, right. So now we have the 3 lenses here, address lens, person to address, age and name as before. And we also now have city lens from address to string and the country lens from address to string. So that's just something to be aware of, that if you do these splices, basically you can't have like recursive definitions that use something that comes after the splice. Let me just see whether I forgot anything important in the, okay, demo I did. Okay, fine. So we are done with the splices. So I still have half an hour for quasi quotes, which is nice. Right. So I don't know all these types, but it's just important. Or if you ever want to do something with template Haskell, want to do this yourself, it's good to know that that exists. So you can, it's like, what's it called in C#, for example, it's called reflection. So you can basically look at a Haskell type or Haskell value and inspect it, find out how it's defined in the case of types, the constructors, the arguments to the constructors, and so on. And that is then used, for example, here, when you automatically make lenses. Because obviously, how is that supposed to, where does this code come from? How does the lens library do this? And the lens library will in its template Haskell module use this reify. So it takes the name like person or address, use reify to get to the definition, and then find out, okay, this is a record type, had fields that are named so and so, and then generate this code automatically. So that's an important feature of template Haskell, that you can inspect definitions of values and types. Right, there's two things I want to show you. One is another example of how to use it. And that uses this Shakespeare, but I think I had an example somewhere. Maybe I have it already in the code. Of course not. I did have it, I think, and I deleted it. Do you know, Robertino, or did you want to show that anyway in the next lecture?
In the next lecture, I'm going over Blaze HTML and HSX, which is
So
legit.
is
Yes.
that using template Haskell?
Yes.
Okay, so then I don't have to do that example here now. Then you
Sure.
will do that, right?
Yeah.
So I mean, maybe just briefly. I mean, first of all, on Thursday I won't be available, so Robertino will do the lecture, and that will be about web programming in Haskell. So hopefully, a very fun lecture. And one of the things is you can easily generate HTML with Haskell, and that works also with template Haskell. So you can basically write something that looks like almost like HTML, and then template Haskell is used to actually convert it into like proper HTML, but just as a teaser. So the last thing I want to talk about is quasi quotes, which is also very cool, I think. So that's another application of template Haskell, or an extension. And basically it means you can extend Haskell syntax arbitrarily. So today we looked a lot at these Oxford brackets, and we saw a couple of varieties. So we saw typed expressions, untyped patterns, untyped declarations, and so on. But quasi quotes allows you to extend this with arbitrary things. So you can define your own Oxford brackets, basically. And there can be arbitrary strings in an arbitrary format between them. And you tell the compiler how to interpret that. And that's called quasi quotes. So for example, that's used for example, what I just said, HTML, but anything. So you can have arbitrary strings and basically pass them and then interpret that as code in some way. And I have one example for you. And I just want to motivate that. That's just a second. Right. If we now load quasi. In Haskell, literals. I mean, normally we write decimal literals. So let's say we have 42 decimal int. Drives insane. 4210 is an int. Of course, like this, right? I mean, this is obvious. Why is this giving me an error? Because of this. Maybe I have it. Anyway, doesn't matter. Okay. But what we maybe haven't talked about yet, or probably haven't talked about, there are other forms of literals. For example, you can use hexadecimal in Haskell as well. So base 16, and then you write 0x, and then whatever. What is this? This is 2 times 16 plus 10. Plus 10. So this is also valid Haskell. And there is also octal. So base 8. I think that's with an O. So what would that be? 5 times 8 plus 2. And I mean, of course, they are all the same number, right? It's all 42. And there's also binary. Two. However, so that would be 32 plus 10, so no 16, 1, 8, no 4, 1, 2, no. However, that requires an extension, I think. Maybe the GHG version is too old. No,
It could
right.
figure
Yeah,
out by
no, it's fine. It's fine. It works. Right. So there's an extension for that if you want to use the 0b thing. But nevertheless, so that's the built-in or supported, sort of supported ways to write numeric literals. So base 10 is the usual one, but you can with 0x you can use hexadecimal, with 0o you can use octal, with 0b you can use binary. But what if we wanted something that's not in this list? So for example, ternary, base 3. And with quasi quotes, that's possible, like so. So first of all, I mean, that has now first nothing to do with template Haskell. Just in general, I mean, if we have a string and we want to pass it as a ternary number, so ternary base 3, there are 2 digits, 0, 1, 2. And the passing works just as for any other number system. So that's like primary school, actually. So we just, this is just for one character. So we just fold from left to right. I mean, this is an example here. If you read something like 1120, so the powers of 3 are 1, 3, 9, 27. So it's 1 times 27 plus 1 times 9 plus 2 times 3 plus 0 times 1. And this is just what I did here. Okay, so far so good. I mean, this has nothing to do with template Haskell. That's just so I can use pass ternary and 1120, and that's again 42. Okay, and now I want to extend Haskell so that I can use ternary number literals, and that's where quasi quotes come in, and they are defined as follows. So there's a term quasi quota that should also be here. If we look for quasi, I'm still in lenses, sorry. It's of course in template Haskell. If we use for quasi quota, and that's just a record type, and it basically, it's very flexible. So in principle, I can use quasi quotes for expressions, for patterns, for types, and for declarations. But most quasi quotes out there won't make sense for all of these. And in that case, you just throw an exception. So it's, I mean, looks like weird, but that's how people do it. So you don't necessarily support all 4. So in our case, so we want a quasi quota that can interpret like ternary strings as literals, as integer literals, or more general as numeric literals. And where do numeric literals make sense? Well, they certainly make sense as an expression, and they make sense as a pattern. I mean, I can have them on the left-hand side of an equation when I define something, so then it's a pattern, or I can have them on the right-hand side as an expression. They don't make sense as a type, and they don't make sense as a declaration. So in my case, for this example, I would define those 2 fields here, but not those 2. And then you just, so I just define this record, and then I tell it, okay, how do I, a given string, how do I pass it as an expression? How do I pass it as a pattern, as a type, and as a declaration? So for type and declaration, I just throw an error and say, doesn't make sense. And for expression and pattern, I basically use my helper function, pass ternary, and then just use what we did before. So in order to get an expression, so given a string, I use my helper function to get the int, and then just use Oxford brackets as before to express this int as code, as an expression. I could, of course, also use this lit e constructor explicitly, but I mean, normally if you can use quotes, they are nicer. Here for the pattern, I actually use the lit p. In principle, it should also be possible to do this, but I think I tried it and it didn't work for me for some reason. I mean, it should be possible to do it like this, but then it somehow complained for whatever reason, don't know.
Right.
But like this, it works. So I explicitly built a literal pattern of an integer literal n. Right. So this is the definition. And this doesn't tell you, of course, so, and I call it ternary. So now how do we actually use this thing? So again, you must, if you want to use a quasi-quota, it must be in a different module, same as for splices, template Haskell. If you want to use them, you must activate this quasi-quotes extension. Oh, there's the Blaze example, actually. But I don't show that because you will show it. Now I found it. Right, so anyway, maybe I can still. Right, and now how do you use it? So here are actually these examples, so I knew I had them somewhere. So I can delete them here. Anyway. Okay. So I mean, this is what we saw, 2, 8, 16, 10 is missing here. But now in order to use my new one, so as we saw before, so there are these Oxford brackets and basically built in is without anything between the bracket and the vertical bar for expressions, or you can also optionally use an E, then P for pattern, D for declaration, T for type. And now with this quasi-quote mechanism, you can put arbitrary stuff there. So I defined this ternary quasi-quota. So now the syntax is opening square bracket, then the name of my quasi-quota, vertical bar, and then string, and then I close the Oxford brackets. And now this is like a piece of syntax that I now defined. So now when Haskell is, and this is now used as an expression, right? This is an expression. And here I use it as a pattern. So I have this weird function from into string. And here I use it on the left-hand side of the equation of the equal sign as a pattern. And if we load the module, use it, do it again. Sorry, right, it worked before. So now we see that where here 42, this ternary 1120, what is spliced in is the literal 42. So at compile time, this so-called quasi-quote is basically evaluated. So my code runs for the definition of this quasi-quote. It runs this helper function, it passes it as the integer 42, and then splices 42 at this point in the source code. So this is exactly the same as if I had written 42 here. So at compile time, it replaces this thing with 42. And same here. So we see the other splice here in line 19. So this here is exactly the same as if instead of this quasi-quote, I had written 42 here. So this is, I mean, very nice somehow, because it means you, in principle, it means you can extend Haskell with arbitrary syntax. So, I mean, it's completely up to you how you interpret the string between these, I mean, in these Oxford brackets. So you can have your own language or programming language or whatever, and then you write a parser for it, and then you basically splice the result into your code at compile time. So there's no runtime overhead for this. Of course, you could also like just use this helper function directly, but then it would incur runtime overhead, because each time then it's not a literal. I mean, it has to do computation at runtime. But this way, it is exactly as efficient as if you had written 4 and 2 in the first place. And yeah, here's also this example to make it just briefly. So one cool application of quasi-quotes is the so-called Shakespearean quartet or triplet. So there's one for HTML. So it's called Hamlet or S Hamlet, because I think they all start with S, and then it's Hamlet and others for JavaScript and stuff. So basically it looks like this, and then you can write something that looks like HTML, but note that it's, for example, this HTML tag is not closed. So this is this special syntax here that this quasi-quota can handle. Then if you look at the splices, we see that this is actually generated. I don't see the here. So this is what's actually generated. So now it's proper HTML. With HTML, the tags are closed as a body tag that's closed again, and so on. So yeah, that's this quasi-quota, which makes it easy to generate HTML, for example. So this is, I think, really cool. And just the other day, I was playing with ChatGPT and generating prompts. So there's actually, I didn't use it for that, but I could have. So there is a quasi-quota to for multi-line text. There is no very good multi-line text support in Haskell, not built in. So if you have like text that spans over several lines, like literal strings, it's I mean, normally you have to do something uh, like this. My long string. This is the first line. Here is the second line, and so on. So you always have to, and a third. So there's no way in Haskell to do this basically without, I mean, a string can't be longer than a line. So if you need strings that are longer than a line, you basically have to like split it into single line strings and concatenate them. And there is a quasi-quota whose name I now forgot, but it's, let's see, string interpolation. Package. I forgot the name again. I mean, there are several ones. I think this one. Yeah, I think it was that one. Data string interpolate. So it not only can do multi-line strings, it can also interpolate. So like you're used to from JavaScript or so. So here's an example. If age is 33 and name is Tatiana. And it also works not only with string, but also with text and other like string-like types. And then you can have this I quasi-quote and use something like this to generate like JSON, for example. And that also works with like, so there are certain variations, but you can also do it with multi-lines. So then everything in this quasi-quote, including the new lines, is then one big string. And you can even interpolate, like plug in variables at some points. So that's actually quite nice. So there are lots of examples for or applications for these quasi-quotes as well, especially if you do something like HTML or SQL or JSON or for config files or whatever. So in that sense, Haskell syntax is extendable. Just want to see at the slides whether I forgot some very right. So just to sum up, so template Haskell, I mean, one application is to get more control about optimizations, to so at compile time already write optimized code, for example, and make it possible to use abstractions with zero overhead at runtime. And it is very safe because of this typed way. So when you write it, you immediately get errors if you make a type error. And there's untyped Haskell, which is extremely powerful. You can generate arbitrary code, but it's also tricky to debug and maintain. And because it has access to arbitrary I/O, it's also quite dangerous. So some people don't like to use it for that reason. And then there are these quasi quotes, which in principle allow you to use to extend Haskell with arbitrary syntax. So using a quasi quota, it's completely up to you. I mean, for example, I had now this ternary example. I could also turn my tuple example into a quasi quota, and yeah, if I wanted to, and then use that the quasi quote can also do declarations, and I could whatever write some arbitrary string there, and I mean, depending on how I pass it, uh, define functions for that and so on. So yeah, you can in principle write arbitrary code, generate arbitrary code with template Haskell, but it can be quite tricky. I mean, I personally have never done it in production. I mean, used it, of course, like for lenses, but not actually like generated it myself. I think generics, for example, I have done that like for real. And I think that's relatively doable and relatively simple. If you have like type class for whatever serialization to give generic support is quite doable and easy once you understand the principle. I think template Haskell to add deriving for class instance and so on is certainly more difficult than for generics. And yeah, and also some people don't like it to use it. And I think it also has an impact on like compilation times. Not only if there are like elaborate computations during compilation, but also if template Haskell is used, then often you have to do more recompilations of modules because then GHG can't be sure that, I mean, these splices can change, right? And I think GHG is not very smart about, so it's very conservative in that sense. So when template Haskell is used, it's basically recompiled all the time because, I mean, it can use arbitrary I/O, so it doesn't know, I mean, something could have changed. So yeah, there's also that. So people are often not very happy to use template Haskell, but it has, I mean, it is very powerful. And because, I mean, it's spliced in and then the compiler is run. So, I mean, you can't generate a code with errors with that because the compiler always checks it. I mean, we saw the warnings in my first example pop up that I didn't have type signatures, for example. And if I made a type error somewhere, then, I mean, it wouldn't compile. Yeah, so it's very powerful, but also not so easy, but it's easy enough to use, for example, for lenses. I think I should stop here. Are there any questions?
Not so far, but maybe we can wait 1 minute.
Of course. And maybe I can say, so I briefly mentioned, so on Thursday I won't be available, but Robertino kindly agreed to do the lecture. And I think that will be a very fun lecture. So I think you will do a complete web application.
Yes.
Yes, in Haskell.
Yeah, hopefully it will be fun.
Mhm,
I will try my best to make it fun.
very good. And that's then it with Haskell. So, I mean, of course, there's much more to say about Haskell, but I mean, we want to get to smart contracts. So then next week we'll start with Malo, which is very easy. I mean, after all you have learned now about Haskell, I mean, it doesn't have much to do with Haskell, but I mean, you can use Haskell to write it, but that will be very easy for you with what you know now, because Malo uses very simple Haskell that in principle after 1 week of Haskell, you could do Malo. And then we'll turn to Plutus for the remainder of the course. And yes, but that's also, I mean, everything you need regarding Haskell for Plutus we have covered. I mean, template Haskell is also used a bit for Plutus, but we have seen that now today. And I mean, you just have to use it like I did for the lenses, not write your own template Haskell code. So that's all straightforward. And yes, but I think you now know, I mean, in principle, I mean, if you understand everything that we taught you, then I think you know more than enough to work as a junior Haskell developer somewhere.
Yes.
And it's definitely much more than most introductory texts into Haskell cover. So it's like quite advanced, some of the things we did. Of course, there are still, as I said, some gaps. I mean, for example, we talk about web programming. We didn't mention databases. So there are various ways to do persistence in Haskell. So you can interact with, I mean, and it's like also on different levels of sophistication. So there are quite low level ones where you can interact with SQL databases where you more or less write your queries by hand, maybe using something like quasi quotes. And there are more sophisticated ones where it's very type safe, where in principle, I mean, you somehow define the database schema and then the plumbing is done automatically for you. There's also one that I like very much. It's called Asset, I think, Asset State, which doesn't use a relational database. Instead, it basically uses Haskell types for persistence, which I personally use in my own projects a lot because I think it's really nice. Right, so we haven't talked about that. And then, of course, you can also do graphics and music and whatever in Haskell. But I think and then, of course, there's type level programming, which we also didn't cover. So especially in recent years, you can do a lot on, I mean, the type system has become quite advanced. So you can do really cool things. For example, you can have a type of lists of a specific length, like lists of length n or 7. And then things like in the type system, you know that if you concatenate a list of length 7 with a list of length 3, you get a list of length 10, things like that. Which is also quite cool. For example, there's a very nice web library called Servant. And you basically your API, your REST API is a type. So you encode the whole API as a type. And then so the type specifies what type of endpoints you have, what they are called, what parameters they take, whether they are get or post or delete or update or whatever. How the data is serialized, whether it's JSON encoded or plain text or something else. And then once you have this type, you basically can write handlers on the one side, on the server side, that serve requests to this API. But you can also automatically generate the client side, for example, in JavaScript, that will then be able to communicate with the server. Or you can automatically generate documentation and things like that. So there are, I mean, there are very nice applications for this type level stuff. So we didn't get into that. I mean, the most advanced type level things we did was GADTs, where we talked about free monads. So yeah, there's more to learn if you're interested, but I think you have in more than enough as a foundation to basically get a job as a Haskell developer, junior Haskell developer. Provided, of course, you did your homework and your exercises. Okay, still no questions?
No.
Okay, fine. Then as I said, next Thursday it's Robertino, and then in a week I'll give an introduction into Marlow, one of the 2 smart contract languages on Cardano. Okay, then thank you very much, and I'll talk to you in a week.
Thank you.
Thank you.
Thank you.
Bye.
Bye.